So next we are going to see behavior of magnetic materials. So here the angular momentum of an electron. So your material is nothing but made up of atoms. So each atom consists of electron particle. So the angular momentum which is present in the electron will be called as spin. Okay. I think you all know electron is nothing but charged particle. The spin of the electron produces magnetic dipole moment. So in an atom, it's completely filled orbit. The contribution in spin magnetic momentum will be zero. So in other words, we can say that the spin of the electron in the incompletely filled cells contribute more in the resultant spin magnetic moment. Okay. So the angular moment of the electron will have the spin of the electron. So the spin of the electron will produce the magnetic dipole moment. So similar to electrospin, the nuclear spin also contributes to the magnetic moment, which will be called as a nuclear spin magnetic moment. So the mass of the nucleus will be larger than electron. So the dipole moment due to nuclear spin will be very small. So the contribution of nuclear magnetic moment to the magnetic properties of material can be neglected. Okay. So here the total magnetic dipole moment of an atom can be calculated by adding all the magnetic dipole moments which we said now. Okay, in appropriate manner. Okay. So that is nothing but we are going to all the magnetic dipole moment which is the with the electron as well as in magnetic moment. Okay. That will give the total magnetic dipole moment of your atom. Now we are going to see classification of magnetic material. What are the magnetic materials available? Okay. So here, based on your magnetic behavior, your magnetic material can be classified into diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, perimagnetic, and supermagnetic. Okay. These are the classifications of magnetic material: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, perimagnetic, and supermagnetic. Okay. So one by one we are going to see what is diamagnetic material. So the magnetic material in which the orbital magnetic moment and the electron spin magnetic moment cancel each other. Okay. So the magnetic moment due to orbital as well as spin will be getting cancelled to each other to produce the permanent magnetic moment as zero. It will be called as a diamagnetic material. Okay. Orbital moment as well as spin moment get cancelled to each other to give you zero value for next magnetic moment. Okay. Next permanent magnetic moment. So magnetic moment present in this material will be zero. Okay, simply we can say. That will be called as a diamagnetic material. If you apply electric field to the magnetic material, what will happen means it will oppose, that is the magnetic moment which is present here, it is very minute, that will oppose the applying field, that is electric field. So that here the diamagnetic material magnet gets repelled. Okay, gets repelled due to the presence of electric field. Okay, so example of diamagnetic material is lead, copper, silicon, diamond, graphite, sulfur, sodium chloride are inert gases. Okay, this is said to be diamagnetic material. The next we are going to see about the paramagnetic material. Here the orbital moment as well as spin moment do not cancel each other. மேல பார்த்தீங்கன்னா diamagneticல பார்த்தீங்கன்னா it will be cancelling each other. Orbital moment as well as spin moment will get cancelled to each other. But இங்க வந்து பார்த்தீங்கன்னா it will not cancel. Yeah. So that the next magnetic moment will we will be having some next magnetic moment. Okay, sorry for the interruption. So the magnetic in which magnetic material in which your orbit moment as well as spin moment they cancel each other to produce some more magnetic moment in the material which is called as paramagnetic material. Here, if you apply electric field, then here it will produce some dark as well as dipole moment, which will be aligning with the external field, so that the moment which is present in the material will attract to each other. Okay, it's attract with the strong manner which is developed in the surface. Okay, here it will be attracting, but in the diamagnet it will not attract, but it will repel to each other. Okay, so for example, potassium, tungsten, oxygen, rare earth method will be coming under the paramagnetic material. Okay, say the difference between these two materials, that it will be that the orbital and the spin moment will be cancel each other, but here it will not cancel. So that in here it will be having some magnetic moment. So while you are applying the electric field, the strong material, that is magnetic material, will attract the moment. Okay. So example of both will be given here, and then அடுத்தது ferromagnetic பார்க்கலாம். Ferromagnetic electric field, the atoms will have large dipole moment due to spin moment. Okay, that will be called as a ferromagnetic material. So here the moments, dipole moments will be arranged in a parallel. Okay, that will be called as a domain. So இந்த மாதிரி parallel தான் இருக்கும். So diagramல கொடுத்துருக்காங்க. Parallel dipole moments will be arranged. That will be called as a domain. So parallel after domain னு சொல்லுவோம். ஒவ்வொரு parallel set of parallel dipole moments will be put here. So that each parallel dipole moment will be called as a domain. So while you are applying current, this electric field or external field, the domains will be increasing their size. Okay. If you remove the external field, what will happen is the random element will be in the original size. Okay. If you apply the external field, then it will get, the size will be getting increased. Okay. So some of the moments will be in the small region, which will be called as a residual field or remnant field. This effect will be called as a hysteresis. For example, iron, nickel, and cobalt will come under ferromagnetic material. Okay. So when a current carrying in the wire or conductor, which will be creating the magnetic field. Okay, the current carrying the conductor, which is found on the magnetic material, will produce a magnetic field. Here, the magnetic field will have magnetic dipoles, which will be aligned in the direction of the magnetic field. So the domains and parallel dipole moment will be called as a domain. Okay. So the domains in the material which are already in the direction of magnetic field will get increases when you are applying the electric field, okay, or external field. The size of the domain will be getting increased. Okay. So the remaining domain will be rotating their dipoles in the direction of magnetic dipole. The dipole which is growing in size will be growing with respect to your neighboring domain. So the magnetic flux density which is generated due to the magnetic material increasing will be calculated based on your relationship, that is D vector equal to mu vector dot H vector. Okay. So in this manner you will be relating that magnetic flux density with your magnetic flux intensity. Okay. Flux density வேற intensity, magnetic field intensity வேற. Okay. So the materials in which the dipole moment of adjacent atom line up in anti-parallel charges. parallel dipole moment arrange ஆயிருந்தா அது வந்து என்ன ferromagnetic material. இதே வந்து anti parallel அந்த parallel இல்ல அப்படின்னா it will be called as a anti ferromagnetic material. Here the magnetic moment will be zero. Okay, the net magnetic moment in the anti ferromagnetic material value will be zero. So now we are going to the example of anti-parallel magnetic material or oxide, chloride, sulfide, everything which is going to be acting the low temperature will give the anti-ferromagnetic property. Here we are going to consider the current IB which is flowing in the conductor in a closed path. Okay, which will enclose the differential area ds vector. Then the magnetic dipole moment generated here will be calculated as m vector. This dipole moment is represented as m vector, small m vector equal to id into ds vector. So id is nothing but the current flowing in the conductor, ds is the differential area. Okay. Now we are going to use this dipole moment in the volume, differential volume del V. Okay. So the total magnetic dipole moment will be achieved by summing of all the magnetic dipole moment in individuals. Okay, that is represented by m vector total equal to summation of 1 to a equal to 1 to n del v. Okay, into m vector a. So a represents nothing but this is your numbers. Okay, number of system added. Sorry, number of dipole moment added to the added to your volume of material. Here the magnetization can be represented in the form of m vector. Okay, magnetization is nothing but magnetic dipole moment per unit volume. Okay, so unit of magnetization is ampere per meter. So the formula for magnetization is m vector, capital M vector, small m will represent dipole, magnetic dipole moment. Here capital M represents magnetization. Limit del V tends to 0, 1 by del V, summation of A equal to 1 to n del V m A vector. இதே equation தான் இதுல வந்து நீங்க வந்து லிமிட் அப்ளை பண்ண போற. Okay. So we can write the relationship between V vector, H vector and M vector as, so V vector is the magnetic flux density, H vector is the magnetic field intensity, M vector is the magnetization. We are going to relate each other by an equation, that is V vector. Either V vector equal to mu naught into H vector plus M vector. Okay. So for linear isotropic magnetic material, we can write the magnetization as psi m H vector. So psi m quantity is nothing but magnetic susceptibility, which is dimensionless. That is unitless. Okay. So now we are going to substitute the equation 11 in 10. Okay. So substitute pannina and the must be correct. Mu naught into H vector plus psi m H vector. Illa H vector formula ku veliya eduthinga 1 plus psi m. Okay. So but for any magnetic material, you can write the V vector equal to mu H. Idna unnoru V vector and H vector ku relate panni. V vector equal to mu H. So mu is nothing but permeability. Mu naught into mu on relative permeability and permeability of 6 degrees. Okay. So mu naught into mu naught extend பண்ணிக்கலாம். இப்போ வந்து என்ன பண்றோம், இது ரெண்டையும் நம்ம கம்பேர் பண்றோம். 12th and 13th equation கம்பேர் பண்ணலாம். கம்பேர் பண்ணா you can write mu r as 1 plus psi m எழுதலாமா, mu naught mu r h, mu naught mu r h. Okay, so mu r பதிலா இங்க 1 plus psi m னு ரிப்ளேஸ் பண்ணலாம். அப்ப mu r ஐ இதோட ரிலேட் பண்ணலாமா. So mu r equal to 1 plus psi m is nothing but mu by mu naught. ஏன்னா mu equal to mu naught into mu r. அதுல வந்து mu r one side வச்சிட்டீங்கன்னா mu by mu naught தானே. So mu by mu naught will give 1 plus psi m. Okay. So mu is nothing but permeability of the material which can be measured in unit Henry per meter. Okay. Next we are going to see magnetic boundary conditions. So when you are traveling, that magnetic field traveling from one medium to another medium, you must consider that boundary value. Okay. That will be called as here boundary conditions for magnetic materials. Here you will be having two boundary components, that is tangential to boundary and normal to boundary. Okay, tangential to boundary means it will be like a parallel line. Okay, a normal to boundary means it will be perpendicular to the medium. Okay, so here we are going to consider two boundaries. So we are going to consider a boundary between the two isotropic homogeneous linear materials with different permeabilities mu1 and mu2. So ஒரு மீடியமோட permeability mu1, இன்னொரு மீடியமோட permeability பார்த்தீங்கன்னா இந்த மீடியம்ல இருந்து பண்றப்ப changes for the medium. Now we are going to determine the boundary conditions. Since the picture is most part of your medium. Now we are going to see the boundary conditions for normal components. Here we are going to consider right circular cylinder surface. In this, height of the cylinder will be L such, so that half of the height you will be placing the medium one, that is del h by 2. The remaining height del h by 2 will be representing medium 2. Okay, the axis of cylinder will be in the normal direction to your surface. So according to your Gauss law for magnetic field, you can write the equation as integral of B vector dot ds vector equal to 0. This is nothing but Gauss law of magnetic field. So on taking surface integral for the whole cylinder, right, circular cylinder, you will be considering three surfaces, that is top, bottom and lateral surface. Here the lateral surface can be taken as a 0 value. The very important part will be top and bottom. Okay, so அது மட்டும் தான் நம்ம consider பண்ண போறோம். So top surface பார்த்தீங்கன்னா you can write that equation as Gauss law as for the top surface as integral of B vector dot ds vector equal to Bn1. So n1 represent normal magnitude of normal component. Okay, so அதனால Bn1 integral of ds vector. So here this will be a magnitude component. So we are going to take out of integral value. So Bn1 into integral of ds vector. So simply integral of ds vector can be written as del s. அதே மாதிரி for bottom surface, integral of bottom surface or here B vector dot ds vector. அதே மாதிரி normal component can be written as Bn into vector, integral of ds vector. So integral of ds vector simply you can write it as here del s. Okay, so top surface bottom surface ஓட டாட்ஸ் நான் எழுதிக்கிறீங்க. Then for lateral surface you are going to consider that value as a 0. Okay, Gauss value 0 னு எடுத்துக்கிறீங்க. So you substitute all the value in the equation 2. So இதுல substitute பண்றீங்க. So all the three surface value, okay, will give the magnetic field intensity value, will give the 0 value. Okay, so அந்த equation எடுத்துக்கிறீங்க. எடுத்து apply பண்றப்ப இங்க மைனஸ் வரும் பாருங்க. நம்ம இங்க பிளஸ் தான கொடுத்துட்டோம், பட் இங்க நம்ம மைனஸ் கொடுத்தோம். ஏன் மைனஸ் ரெப்ரசன்ட் பண்றாங்கன்னா ஒரு மீடியம்ல வந்து என்னாகும், ஒரு மீடியம்ல இருந்து இன்னொரு மீடியம்க்கு தானே டிராவல் பண்றீங்க. மேக்னெட்டிக் ஃபீல்ட் இருக்கும் from one medium to another medium. அப்ப என்னாகும், ஒரு ஃபீல்டு மீடியத்தை வந்து லீவ் பண்ணுது, இன்னொரு மீடியம்ல என்டர் ஆகுது. ஒரு மீடியம்குள்ள விடுது, ஒரு மீடியம்குள்ள நுழையுது. அப்ப ரெண்டு ஆப்போசிட் டைரக்ஷன்ல தான் வரும். Okay, the magnetic field will be magnetic flux lines or field will be in the opposite direction. So that we are going to write the minus sign for the field 2. Okay, அப்ப இந்த இடத்துல மைனஸ்னு வரும். இப்ப பாரு ஈக்குவல் டு 0 தானே, அப்ப அப்போ இந்த சைடு இந்த ஈக்குவேஷன் கொடுத்தீங்கன்னா இந்த டேர்ம் கொடுத்தீங்கன்னா bn del s is equal to bn to del s. So finally you can write that del s cancel பண்ணிட்டீங்கன்னா bn1 equal to bn2. Okay, thus the normal component of B vector is continuous at the boundary. So same normal component of B vector. B vector is nothing but magnetic field intensity is continued at the boundary also. Okay, the magnetic field intensity does not change at the boundary is represented in the equation. Okay, bn1 equal to bn2. ஏதாவது வேற some value factor multiply ஆயிருந்தா there is a change in the boundary value ன்னு சொல்றாங்க. இங்க வந்து எதுவுமே சேஞ்ச் ஆகல. The same intensity is followed in the boundary also is represented in the equation. சரியா? So as the magnetic flux density and magnetic field intensity can be related by the equation B vector equal to mu H vector. So B vector ன்றது magnetic field magnetic flux density, H vector ன்றது magnetic field intensity. So equation 7 can be written as mu1 H n1 equal to mu2 H n2. Mu H V க்கு பதிலா mu H. Okay. represent பண்ணிட்டோம். So இதுல இருந்து H n1 H ஒரு சைடும் mu ஒரு சைடும் போட்டு போறீங்கன்னா you will be writing this 8 equation. சரியா? So finally you can determine that the field strength in two medium are inversely proportional to their relative permeability. Relative permeability. Inversely proportional. Now Hn1 value mu1 வந்து denominator அப்ப inversely proportional to the relative permeability. Okay, n2 பாத்தீங்கன்னா numerator mu2 value. So opposite the inversely proportional to their relative permeability. Okay. Next, boundary conditions for tangential components. So similarly, you will be calculating magnetic flux intensity and density for the tangential component. Here you will be applying the Ampere circuit law. So what is Ampere circuit law? Integral of H vector dot dl vector will give current value. Okay. First part you will be applying this boundary value, that is Ampere circuit law. So summation of all this value. Okay, first part is nothing but A B C D A. Okay,